Hello and welcome to the next episode of how to make an operating system in Rust. Last time we basically started multiple cores. There was one thing that I forgot to do, and we're gonna do now. First, let's check up the stack size to 46 and make another constant, numprox CU size equal to 4. We have 4 processors, and now we need to multiply we need to multiply the size of the stack by the number of processors. Otherwise, we're gonna overwrite, and that is also a big reason why it's worked so inconsistently last time. So this is the stack. Now we allocated it. Now we just need to go into boot.rs. And let's actually grab this where we get the processor core, like the number. Let's grab that and put it at the start. And I'm gonna say get processor ID. Okay. And now that we have the processor ID, we're gonna actually put this in X9 arbitrarily because we're gonna use it later. Okay. So now that we got the processor ID, what we need to do is we need to multiply the stack size by the processor ID. Let's see. So we get the address of the stack. We move the stack size into X8. And then add it on top. What we want to do is actually add X9 and add 1 to it. And then multiply X8 by X9. So when processor core 0 starts, I'm gonna add 1 to it. It's gonna multiply the stack size by 1. And then it's gonna add it to the SBE. This should work. So let's see. Build and run. Okay. This looks pretty consistent. Okay, what we're gonna do now is we're gonna say, instead of doing else, we're gonna let every processor print. Okay, it looks good. Core 0, 3, 2, and 1. The next thing that we need to do, now we see everything is garbled, right? That is because we are writing to the same device with the same, with multiple processors. And to actually to synchronize all of that, we need something called a mutex. So my mutex implementation, let's start by mutex.rs. My mutex implementation is going to be based on the following. This blog post by William Henderson. I'm going to link it in the description. I'm also going to put it into the code as a comment. So based on this, and now to implementing this, what we're going to do is we are going to define a struct, call it mutex, and it's going to take a type T. So it's going to be a generic struct. And what do we need inside of the mutex? Inside of the mutex, we need a variable that says, is the mutex locked or not? That's going to be an atomic bool. Atomics are basically values that can be safely modified in one operation on multiple cores. So normally, if we modify a variable by putting it equal something, what happens is the compiler is gonna load the variable into a register. Then it is gonna modify the value in register and then store the value back from the register. And now what we need to do, why we're using an atomic, is that these three instructions can be basically interrupted by another processor. What happens if another processor loads while the first one is modifying in? It's not stored yet, so that means it's gonna it's gonna load the old value and not the modified value. The atomics get around that by doing a load and modify and store in one instruction. So that's why we're using atomics here. Okay. So the next thing that we need is a value that we want to guard. And that value is actually going to be in a structure called an unsafe cell. An unsafe cell basically allows us to mutate the value on multiple threads without having a mutable reference to it. What that means is it's called in Rust's interior mutability. And it just means we can dereference this value without getting a mutable reference to it. That is very important because otherwise we couldn't implement the mutex like this, since we cannot share multiple mutable references with multiple threads. So, or multiple mutable references cannot exist at all. Okay, the next thing, what I'm gonna add here is gonna be the CPU number, and I let's see, we have a value at the CPU number. If the value is locked, I'm gonna make this an atomic. Yeah, let's make it an atomic U8. Or yeah, that should work. So next thing that we're gonna do is we're gonna say impl of T for mutex type T. And the first thing we need is a constructor. Or actually, can we put an option here? Let's actually forgo the CPU field for now. We're gonna add this later. To do add CPU field. The CPU field is only important to see which core currently holds the lock. And if we try to release a lock that is not currently held by us, we will panic in this case. But for now, we're gonna forego that and implement that later. So what we're gonna do is we're gonna make a function new that is gonna take a value t and gonna return a self. And in this function, we're just gonna construct our mutex. So we're gonna say locked is an atomic bool new false. Standard is not locked, and value is going to be an unsafe. Cell new value. Okay, that's our constructor. Then the next thing we need is we need two functions that are acquire and release. So our acquire and release functions are to get ownership of the lock and to release the lock. How are we going to do this? For now, we're just going to spin. So we're going to say while self.locked. And now comes the atomic bool in play. We're going to say compare exchange weak. And we're going to say if the value is false, we're going to set it to true. If it let's see, this is the failure ordering, I think. Let me check real quick. And no, this is the success ordering. So in case of success, we are going to acquire. In case of a failure, we're just going to say it's relaxed. And if it's an error, so if we did not change the value, we're just going to loop forever. So what we're doing here is basically until we acquire the lock, we're just going to loop. Now, what are we going to say in release? In release, we are going to say, let's see. In release, we would normally check, are we the ones holding the lock? So to do, are we the ones holding the lock? If we are, we can just say self.locked.store, and we're gonna store a false with the ordering release. Okay. Now let's import everything that we need to import. So that would be use core cell, unsafe cell is what we used. Use for sync atomic, and here we need atomic bool and ordering. Did we use anything else? We did not. Okay, so now what we're gonna do is we're gonna test our mutex implementation, and we're gonna say here mod mutex, and to test our implementation, what we're just gonna do is we're gonna say there's a static print block of mutex. The type does not matter for now. For now, we're just gonna put u8 in there. It's equal to mutex new. Let's just put a 0 in here for now. So if we now say in unsafe block, if we now say print block.acquire, and here print block.release, we should, in theory, okay, of course we need to use the crate. Okay. Of course, it takes a self. So what we forgot here is the parameter. These are gonna take self. And this one is also gonna take a self reference. We misspelled acquire. Okay, let's see. Unsafe cell cannot be shared between threads. Yes. What we need to do is we need to implement some traits for them, for our spin lock. So what we're gonna say is in mutex rs, we're gonna say a compiler. We're gonna unsafely for impl t. We're gonna say sync for spin, not spin, not mutex. I mean mutex t, where t is send. Okay, what does this arcane magic do? It says, look at our type t. If our type t is send, which means it can be sent to another thread, not shared, but another thread can take ownership of it, which is basically most standard library types. Then we are going to say that for mutex t, this is also going to be sync. So we're basically assuring the compiler that if t is inside our mutex, this is safe to share between multiple threads. Share mutably between multiple threads. Okay, let's try to run this again. We forgot the semicolon here. And now it is running. Let's run it a few times and we see we don't get any garbled output anymore. Very good. So now we have a mutex, but the way you usually use mutexes is you wrap them into another structure called a mutex guard or a lock guard. What that lock guard does is if it goes out of scope, it will automatically release the mutex. So as it is right now, if we acquire the mutex and we don't release it, then the lock will be held indefinitely. We can actually do that and see the output of it. And we see only one core is always printing to the screen because it's never released. This is called a deadlock because one core holds a lock that is important and the other cores are basically waiting on that lock indefinitely. Okay, so now we get to the second part of the implementation. We have a working mutex, and what we're gonna do is we're now gonna implement a lock guard for this mutex. So I'm gonna say mutex guard, and it's gonna take a lifetime of a and or type t, and here we're gonna say there's a lock, and it's of type of a reference to a mutex. So this just means that if our lock goes out of scope, the mutex is still allowed to live until lifetime A. So the reference it might still be valid if our mutex goes not our mutex, if our mutex guard goes out of scope. Okay, so what do we need to implement our mutex guard? This is where the unsafe cell actually comes into place. Since we have a reference here to our mutex, and we're gonna share it between multiple threads, we're gonna make use of the unsafe cell API, I would say, which is gonna give us two different functions that are important for us. There's one deref and the other deref mute, which are basically just gonna dereference the type in the unsafe cell and return a mutable or a not mutable reference to it. Okay, so let's implement this. We're gonna say impl type t deref for mutex guard of some lifetime and type t. And here we're gonna say there's a type, a target of t, and we say function deref self-reference, and we're gonna say we get a reference of t back from this function. And then in an unsafe block, we can just call the API of unsafe cell, which is gonna take the reference for self. We're gonna dereference that, or rather, we're gonna make a reference. We're gonna dereference self block value. So self gives us the mutex card. We're gonna dereference the mutex card and get the lock, and get from the lock the value, and then there is an API call for unsafe cell, which is gonna be get. And this is gonna return us a reference of the value inside of our unsafe cell. The next thing we're gonna do is we're gonna do the same for deref mute. And it's gonna look basically the same, except that we're gonna return a mutable reference. So actually, let's take this away. I don't know what this is for exactly, but it's in my notes for some reason. We're gonna see what happens. So we're gonna take a mutable self-reference and we're gonna return a mutable reference to t. Then it's a similar thing. We're gonna say we get back a mutable reference, dereference self, the lock, and get the value, and we're gonna say get what's inside of the lock. Okay. Now let's try to build this. We forgot the struct. Okay, now we need to also import a core. Use core ops deref and deref mute. Okay, missing target for implementation. That is why I had it. Okay, we're gonna add back the target, type target. E. So this is nice because the compiler basically also already tells us what we need to do. So that's where I got it from. Okay. Now that we got this implemented, we can alter our mutex implementation. And we're gonna say that acquire is gonna return a mutex guard with type t. And here after we acquire the lock, we're gonna say lock, no, mutex card, and we're gonna put into the lock a self. What this is gonna do is it's gonna construct a mutex card and put our mutex into it. Also, I forgot one very important thing that I just remembered. We also need to implement another trait for mutex card. The thing that I mentioned earlier, drop. So when it goes out of scope, we want to do the following. Let's see, this is the same thing. Okay. And we want to fn drop takes a mutable self-reference, and in drop, what we want to do is we want to say self.lock.locked store false ordering release. What this is going to do is it's going to basically call the release function. Actually, we can just call the release function. That should be fine. Let's see if we can do this. Lock.release. Yes. Okay. And now we get, when we acquire a mutex card, but when we say release, let's see. It's gonna be the same, I guess. So we are just not gonna expose release for now, or do we want to expose release? I guess we could. Let's just leave it like this and test it. So what we're gonna do is we're gonna say main rs. In our main rs, we have the mutex u8. What we're actually gonna do is we're gonna put the serial console into the mutex. So let's say we say static serial console, and it's gonna be a mutex of type serial. Now here we want to construct our serial the same way we do it in print. So let's go. Let's see, we're gonna want this. We're gonna yank. Okay, this is not gonna work. So here in print, we're gonna say we want this. And it's gonna be serial adder, I think. It's gonna be not this, but we need to use this. And I think that should work. No, it's not serial adder. Let's see, what did we define? UART adder, of course. Yes, here we need to implement sync for serial. so which is not going to be a problem since it's going to be in the mutex. So what we're going to do is just simply say unsafe impl send for serial, and that should be it. Okay, let's see, can we... Of course, we need to say oh no. I wonder if this is gonna work. This is probably not gonna work. Yes. Can we make this a constant function? I'm actually not sure. Let's see. Yes, it worked, okay. Then I'm gonna say, instead of using kPrintline for now, we're just gonna say here let s equal serial console dot acquire s dot serial underscore pods. It works. And this needs to be mutable. And then we're gonna say, we're just gonna drop the whole thing. So we're gonna scope this. And now what's gonna happen is it's gonna drop the mutex card after this scope is over. So let's see what it's gonna do. It works. And we also get the prints in order. Okay. So what we now can do is in print.rs, instead of always creating a new serial console, we can say that instead of always creating a new one, we will have serial console dot acquire, and this should already work. Then let's see, main. Let's actually get rid of this. Unnecessary unsafe block. Okay, so let's see. Use create serial console. Okay, let's import that. Oh, okay. Then what we're gonna do, instead of defining it here, I will just define it in print for now. So print, we are going to put our static. And let's see if this is going to work. Oh, yeah, oh, of course. I get it now. Yeah, this was, let's see. And we don't have to do that. What we have to do is back to main. We are going to paste it here again. And what we actually need to do is we need to say create serial console.acquire. And there we go. Now we got a serial console that is going to work even with multiple cores. Okay, so what did we do? First thing we did is we fixed the stack. So we have multiple cores. Multiple cores need multiple stacks. So we added a number of processes variable, and we put the number of processes, multiplied them by the stack size. Then also we have a global called serial adder, so constant, so we can just use that one. Then what we did is we implemented a mutex using an atomic bool and an unsafe cell. And then we implemented a mutex guard, which is going to drop the mutex, which is going to unlock it as soon as it goes out of scope, so that we avoid problems when we don't unlock the mutex manually. And then we made our mutex implementation return the mutex guard. Another thing that we can do now is acquires blocking. What we could implement now is a function called try acquire, which is going to take a cell and going to return a result of mutex guard. Or an empty error. And here we can say if self dot locked dot compare exchange weak false true ordering acquire ordering relaxed dot is error, then what we're gonna do is we're gonna say we return an error empty. Otherwise, actually we don't need an otherwise, we can just say this. Otherwise we say we return okay block no mutex guard block equals is self. Okay, and now what we can say is here we're gonna say we're gonna, after the print, serial console dot acquire, and then that y is equal to serial console dot try acquire. And then we're gonna print, we're gonna release the serial console. And then we're gonna print line the whole thing. Debug, and we're gonna say y. And that should be it. This should make it possible to test the whole thing. Okay, mutex guard. Mutex. Actually, did we? Yeah. Okay, it's gonna return a result. Okay, well, let's just implement derive debug and make the same change here. Derive debug. Okay, and here we see now that all of them errored out, but they continued. What we're gonna do now is, instead of acquiring, I'm gonna say try acquire. And we see that we now get the mutex card. Here seems we got an error. Okay, mutex. Oh yeah, okay. It's just garbled as it seems. Is it? It seems like it, yeah. Yes, it is garbled. Why does that happen now? Oh. Yeah, because we try to acquire and release. What if we try acquire and never release? Yep, then it's gonna do this. Okay, but anyway, what this means is that our try acquire function is working, and now we can try to get the mutex, or we can wait for the mutex. So one is waiting for the mutex indefinitely, and the other one returns an error value that we can inspect and then say, okay, if it's an error, we cannot get the mutex right now, we try again later, or whatever we want to do. So yeah, this is the episode, and I hope you enjoyed the whole thing. And I see you in the next episode. If there's any questions, feel free to ask me on Discord. Feel free to ask me in the comments. And I see you in the next one.